All right. Hello, everyone. So today we are going to talk about ECE 335, Lab 5. This is about bipolar junction transistor or BJTs. We are going to work on this lab with two BJT devices. So let's get started. First, I'm going to go over the circuit operation of bipolar junction transistors in NPN and PNP, both types of transistors. We are going to talk a little bit about them, and then I'm going to show you the simulation and the experiment circuits that we are going to simulate and build in the lab and run the experiment on them. So let's get started. So first, let's talk about BJTs or bipolar junction transistors. So as you have already learned that this is again a three-terminal transistor with three different doped layers of semiconductor that are joined together. So it has two junctions and three regions of different doped areas in silicon, or it can be in other material, but for now we are just dealing with silicon here. So if I want to draw the physical structure, it will have three terminals. Let's say this is collector, or I'm going to denote it with C, and this is emitter. In short, we denote it with E, and then the middle region is a base. We denote it with B. So usually a BJT will be in two different configuration. It can be in NPN or it can be a PNP junction transistor. So for now, we will start the discussion with NPN transistors, and then we can talk about PNP transistor and how they are created and how they operate. So for an NPN transistor, you can see that the regions are doped in three different types of areas. So the collector will be the N-type, the base will be P-type, and then the emitter will again be N-type. There will be a difference of doping concentration. So usually the emitters are doped heavily, as you already know, like it's the most concentrated doped area in this device. Then P-type regions are usually, the base is usually lightly doped so that the transport can happen easily for the carriers. And then collector is usually either N or N minus to denote it, just to denote that it's the one of the um, areas where we are not looking at, it's mostly the lightly doped area. And for the PNP case, it's the similar situation. So you will have the N-type or lightly doped N-type base, and then a lightly doped collector, and then a heavily doped P-type emitter. Okay. So in terms of circuit symbol, usually the NPN transistor are denoted in this manner, where let me clear it up a little bit. Okay. And these are the three terminals. So you can see that just like MOSFET, the base is on the left, the collector is usually on top, and emitter is usually on the bottom. And there, to distinguish the collector and the emitter, we usually have an arrow. If the arrow is coming out, then it's the NPN emitter. And if the arrow is going in like this, then that is a PNP transistor. just like how we saw in terms of MOSFETs, PMOS and NMOS had the arrow direction different in the opposite direction. Just like that, this is the uh, direction of NPN transistor and PNP transistors. So the direction of the current is usually going to be the direction of the current is usually going to be um, let me just share it again. Going to be from collector to emitter. So it will go from collector to emitter in this direction. And there will be another current that will go from base to collector. So this current is called IB, and this current is called ICE. Okay, and it's the same for PMOS, but the direction of the current will be the opposite. Okay, so let's go into a little bit of in detail um, operation. So how the collector and emitter actually works. So let me draw a circuit. So this is our base, collector, and emitter. If we want to represent it again in terms of the device region, so this is our base, which is going to be p-type. This is collector, and this is emitter. Both are n-type. So the way you can see it is that there are two diodes, just like uh, in NMOS and PMOS. We can see that there is a PN junction diode in this direction, and then again there is another PN junction diode in this direction from body to emitter. So the way we um, fix the operation, you can either forward bias these diodes, and you can also reverse bias these diodes. So in terms of their whether they're forward biased or reverse biased, we can see like four different combination of operations. So let me draw a table with all these junctions so we can remember how they are operating. So the two junctions that we have in this device, one is the base collector junction, and the other is the base emitter junction. And both are PN junction, and you know when you form a PN junction diode or PN junction device, they usually form a space charge in the junction area, and then it creates a depletion region, which can increase or decrease depending on how we are externally putting a voltage across them. So in terms of um, operation, we can have them in reverse bias or we can have them in forward bias. So let's say we have our base collector junction. It can be reverse biased or it can be forward biased. And then we have our base emitter junction, which can also be forward bias and reverse bias. So let's see, like two of the conditions are really easy to understand when they are both reverse bias. So if we are applying a voltage across this device in a direction, so this is our PN junction. Um, so if we are applying a negative voltage to the collector and a positive voltage to the body or to the base, then we are basically reverse biasing uh, these base collector junction. And in a similar way, if we are applying a positive voltage at the base and a negative voltage at the emitter, then we are also, uh, if we're applying a negative voltage at the, uh, sorry about that. Um, so in terms of reverse biasing both these junctions, what is happening is we are looking at collector, emitter, and base. So since this is an NPN device, we are going to apply negative voltage at the body or the base and a positive voltage at the collector. So this junction, this PN junction will be reverse biased. And then in the similar way, if we are applying a negative voltage to the base and a positive voltage to the emitter, then that junction will also be reverse biased. So in this condition, there can be like both junctions are reverse biased over here. So we can see that there will be no current flowing through this junction. So our ICE will be 0. Okay. So this operation region is called cutoff. This is the cutoff region of operation where there is no current flowing between these two region, and there is no current flowing from collector to emitter. And then let's see the other condition where both junctions are forward biased. So if we are going to flip these two areas, flip these two sources at the body or at the base and collector and base and emitter, then what we're doing is we are basically forward biasing both junctions. So the carriers from the electron, from the electron carriers from the emitter can easily travel, go through this barrier because the depletion region at the base emitter junction will be very thin. So it can, the majority carriers, since this is heavily doped, the emitter region, majority carrier electrons can travel through that depletion region and crowd the base region, the p-type region, where the electrons are minority carrier, and but it's also lightly doped, so there will be very few hole carriers that can recombine with the electron. And since there is a heavy density of electrons that are coming from the emitter junction, this region will have a high density of electron, which can diffuse through the PN forward bias junction of the base collector region. So that junction is also forward bias, so the electrons can travel from this P region to the N region to the collector. So we can see that there will be a large current flowing from collector to emitter. So the ICE current that we can see will be high, and that's why this region is called saturation region. So it's similar to how we discussed in MOSFET. So we have a cutoff and a saturation region. In the cutoff, we have no current from collector to emitter. And in saturation, we have a high current that is going from collector to emitter. But now what happens when we are in these two operating region where one junction is forward biased and the other junction is reverse biased? So let's talk about the first one, which is the base emitter junction will be forward biased, but the base collector junction will be reverse biased. So what happens in that situation, the polarity of the sources, I am going to draw two sources just to make it a little bit different, and sometimes it's easier to understand if we are drawing it this way. So we are going to forward bias the base emitter junction. So this is our collector, emitter, and base. To forward bias the base emitter junction, we need to put a positive voltage at the base terminal and a negative voltage at the emitter terminal. That way, this base emitter junction will be forward biased. And to reverse bias the base collector junction, since we have to put a negative voltage at the base junction and a positive voltage at the collector junction. So in this configuration, we are basically forward biasing the base emitter junction and reverse biasing the base collector junction. And this operation is called a forward active. And this region of operation, the BJT will be conducting, because since we have forward biased this PN junction, base emitter junction, there will be similar to the saturation situation. There will be a huge flow of electron carrier from inside of the emitter to the p side of the base. But we also are not, unlike the saturation condition, we have reverse biased this PN junction, the base collector junction, but it will still flow because of this high density of electron in the p-type region. There is a positive voltage applied at the end, at the collector terminal. So that positive voltage is going to attract these electrons, and they will go through this junction barrier, this wide depletion region, and then the current will be flowing from the collector to emitter. So that's why it's active region, and that's why we will see a current that is flowing through this region and this device, and this is called the forward active. And for the last one, where we are flipping this condition how it is right now, so we are going to forward bias the base collector junction, and we are going to reverse bias the base emitter junction. So in this condition, this is called a reverse active region. So in this reverse active region operation, we will see that there is a current flowing, but it's not going to be that large in terms of with compared to the forward active region, because the highest density of electron that can go from the emitter to base, that junction is reverse biased. So there will be a very little concentration of electron that can travel through this barrier. But this is also forward bias, like this PN junction of base collector is forward bias. So there, if there is an electron, like a couple of electron or a few electrons that can travel from the emitter to the base, those can cross this barrier and go to the collector side. So that's also like conducting, but it's a poor conduction. But the forward active operation in that order, that is a high amplitude of current flowing from from collector to emitter. So these BJTs can work in two types of uh, behavior they can show in the circuit. They can work as a switch, or they can work as amplifiers. So in the cutoff and saturation, you can see that the device will either be off or it will be on, like fully on or fully off. So in those two conditions, this BJT is working as a switch. But when they're in active region, they're either forward active or they're reverse active. In those two regions, they are working as amplifiers, because the current, we will soon see that how this current equation is derived, like the ICE current, with respect to the voltage across the collector emitter region. That current and that current shows a behavior similar to how MOSFET amplifiers behave. So we can see that the current is, these devices are going to be acting like an amplifier with a certain gain in the forward active region and the reverse active region. So that is one of the operations that we are going to observe. So now let me show you some of the region operation. So let's do forward active first. Forward active region. We are going to partially derive the equation, but we're not going to go into too much derivation. We're just going to mention the currents, and then we are going to discuss their relationship and the constants that they involve in the current equation. So let's first think about the forward active operation. So in the forward active region, we are applying a positive voltage between the base emitter junction. So I am only talking about the NPN right now, but we are going to circle back and talk a little bit about the PNP transistor too. So for this condition, let's assume that the forward bias, the BE junction is forward bias, base emitter junction is forward bias, and the base collector junction is reverse biased. So we are applying this voltage across it. So what happens is there will be a current flow from base P side to the N side because this PN junction is forward biased between the base and emitter. So let's say this base emitter junction voltage is VBE, and the current that is flowing from base into the P side, it is IB. So the relationship between these two region will be, we can write it, and then the collector base junction is reverse bias, but there will be a current flowing from collector, which is, let's denote it as IC, and this is the forward current. So we are going to denote it in this manner, IF. The equation we can write is similar to the diode equation, e to the power VBE by VT minus 1. So as you all know, the IS is the saturation current, and the VBE is the base emitter voltage, and VT is the thermal voltage. It is exactly the diode equation that we have previously discussed and studied in the diode labs. So the saturation current IS, this is going to be in the order of 10 to the power minus 8 to 10 to the power minus 9 ampere. So it will be like nanoampere range. So it's a very, very small current, as you know, like reverse saturation current. And VT, we already know it is KT over Q, which is the thermal voltage, and it's approximately 0.025 volt at room temperature. Um, so what this is the collector current equation. So that's the collector current that is flowing from the collector to the emitter. But what about the base current? So the base current equation, we have seen that since this is working as the amplifier, so that current would be a very, very small current that flows. If we are writing it in terms of the forward current, then the relationship is written with this equation. So IB will be equals to IF divided by beta F. So this beta F is the gain of this transistor. It's called forward common emitter gain. And usually this value is somewhere between 20 to 500. Usually we can see like 100 to 200 or 100 to 300. And that's usually the ideal scenario of a BJT, where you will see the beta F or forward common emitter gain is going to be in the order of 100 to 300, or maybe a little bit lower than 100 and a little bit higher than 300, but it's in between those numbers. So if we are looking at this current, so the IC current is coming from collector towards base, and IB current is going from base to the inside the device to the emitter. So if we are writing the emitter equation IE, that will we can write it as a Kirchhoff's law, IC plus IB. And then if we combine these two equations, the IB equation here and the IC equation over here, then we can write it, we can simplify it as IS alpha F e to the power VBE by VT minus 1, where this alpha F is nothing but the ratio of beta F by beta F plus 1. So as we know, like beta F is pretty large, and if you like more than 100, so 100 divided by 100 by plus 1 it is going to be slightly lower than 1. So ideally, we want our alpha F to be between 0.95 and 195 to 1. And that is our ideal expectation of this alpha F constant. And this alpha F is called forward common emitter. Sorry, common base gain. So we are looking at two gains. One is this alpha F, which is the common base gain, and then the beta F, which is the common emitter gain. So in terms of relationship, we can see that IC over IB is beta F, and IC over IE is alpha F. So when we are studying these BJTs, we are going to run the simulation and run the experiment and try to find these two constant for these devices, where we can characterize them in that order, in that manner. So now let's talk about the reverse bias condition or reverse active condition. So if we are creating the reverse active region operation, then we are connecting a source in the collector in this direction, so that that region will be forward bias. The collector base collector region will be, and junction will be forward bias, and then we are reverse biasing the base emitter junction. So if we do that, then we can clearly see that now the reverse current is going to be denoted as IR, which is going to be in this direction from emitter to collector. So that is going to, we can denote it as minus IE. So this minus IE current will be IS times e to the power VBC by VT minus 1. So we can write the base current that is going in this direction. IB is going to be IR by beta R. So beta R is similarly another constant. As you can see that this is the common emitter gain, but in the reverse direction. So this is the reverse common emitter gain. And then similarly, if we write the collector current IC, which will be minus IS by alpha e to the power VBC by VT minus 1. And then again, alpha R, we can write it as beta R by beta R plus 1. Again, the alpha R value can be less than 0.95, but it should be greater than 0. And unlike the beta F, and the beta R value will be much smaller. It should always be lower than 20, because in reverse direction, as I said before, that the current amplitude magnitude will not be as big as the forward active region operation. So the base currents in forward and reverse mode are different due to how we have doped differently these regions. And you can get it. I'm just writing down the equations here just for your reference, and you in your handout, like lab handout, you will also see that these equations are given in their long form. So the simplified equation is also provided in the text that is in your assignment page. If you are interested, please read through that to understand how we can simplify these equations and get to a easier understanding of these devices. So let's now go over to how the IV current will look like. So if we are drawing, as you remember in the MOSFET or the diode operation, we generally derived and we try to develop the extract the IV characteristic curve. So for BJT is also like we are going to extract the same information. We are going to apply a voltage, and then we are going to see if the current, we are going to measure how the current is behaving in the device, through the device. So let me draw like a circuit, ideal circuit for this operation. So let's say we have this PNP BJT. So we are going to apply a base current IB using this source, and then we are going to apply a voltage across the VCE terminal, which is going to create the current IC through the device. So if we are trying to think about it, if our current, we are going to go through the regions, just what I have mentioned before. So if your IB current is 0, then the transistor is basically cut off. So there will be no current through the collector to emitter. So IC will always also be 0. Even though you have a VCE which is greater than 0, there will be no current because the base region is not activated. So that's our cutoff region. Now, if we have an IB current which is greater than 0, and it crosses a certain threshold value, just like it did for MOSFET or it did for diodes, then we are going to get a voltage across the BBE junction. So that voltage is VBE. Once that is in the forward bias region, that voltage is approximately over 0.7 volt. Then this diode, this junction, PN junction is going to forward bias, and then we are going to see a positive collector current that is flowing. So that collector current, we can write that equation beta F IB. But you can see that once you, so this collector current is solely dependent on the base current. So once you cross that threshold value of the base current, it creates that, crosses that BBE voltage barrier, or creates that voltage across the base emitter junction. Then we are going to see this collector current flowing, but it's not dependent on the VCE. So it's independent of the VCE. As long as the VCE voltage is greater than our VBE voltage, we will be in forward active region. As soon as our VCE voltage is less than our VBE voltage, we will move into saturation. And you already know, already have seen what happens in saturation. Both of these junctions are forward biased. So you will see a large current flowing. And for PCE lower than 0, we will see the reverse active region of operation. So if you want to try to draw this plot, this IV plot, so in y-axis we have IC, and in x-axis we have VCE. then we can see that the current will start to grow. And then just like MOSFET, it's going to saturate in the active region. And then it is going to stay there until we cross that condition VCE less than VBE. So these curves are actually for different base current. So let's say this is IB for 10 microampere. This is IB for 20 microampere. This is IB for 30 microampere. So as we increase the current in the base region, we will see the overall collector current to increase, just following this equation where beta F is the multiplier, the gain multiplier, that multiplies with the IB current, and we get an IC current, like different IC current in the forward active region. So the forward active region is this part. So once we go beyond that voltage, this is our forward active region of operation. Basically, as you can see, like it has no effect on the collector emitter voltage. It's just going to be constant. And in the reverse active region, what we are going to see is that similar behavior, like the current will start to increase in saturation. So this is our saturation region when both of the devices are forward biased. So it's similar in the reverse direction also, but you can see like qualitatively the current magnitudes in the reverse active region will be much lower than the current magnitude in the forward active region. So that's pretty much our analysis of the BJT. So we are going to test these devices, how they behave in terms of simulation and in terms of experiment. So let's first talk about the LT-SPICE simulation library, how we are going to define our BJT. So the circuit we are going to use is going to look like this. This is emitter, this is collector, this is base. So let's call this voltage source VBB and this voltage source VCC. This resistor is RC. This resistor is RB. So when we are trying to simulate this, we are going to create this circuit. This is going to be a BJT. When in the parts, when you hit P or if you open the parts window or component window, write down NPN to instance this BJT in your schematic, and it usually is denoted with Q. Once you place your instance, your symbol for BJT, it will be usually starting with Q1 or Q2. So once you do it, usually when you first instance a BJT, it just says Q1 and then NPN. But what we are going to do, we are going to select the number, like the model number. And previously what you did was you opened the component attribute window and then edited that while you placed a model file in your LT-SPICE directory. But here we can pretty much use the devices that we have in the library. There is a library of BJTs that LT-SPICE already contains. So what we are going to do, we are going to use one of those models to simulate our devices. So the model we are going to use is numbered 2N3904. And the way to find it is once you right click on the device and you say add new device, or the window that opens, it has the bipolar transistor Q1. You can select the pick new transistor button. Now, once you hit that, a new window will appear where you can see a lots of models for these BJTs. So from there, you can choose 2N3904 for your NMOS, or sorry, for your NPN transistor. And for PNP, you have 3906 model for the PNP BJT transistor. So you can use those two models to simulate your circuits. Okay. So once you build the circuit, what we are going to do is we are going to first simulate. We are first going to keep VCC at 15 volts, and we are going to sweep VB from 0 to 3 volts, and we are going to observe IB current. And we are going to see how that IB current is behaving. So if we plot it, it usually will look something like, if we plot the IB versus VBE, you are going to see something like this. Okay. So if you sweep the VBB, you can see that the RB and RC are there in the circuit. The RB register is pretty large. In your handout, it says 100K. So if you have a 100K register and you're applying about 3 volts, you can imagine that most of these voltage will be dropping across the RB. But it will be enough voltage to actually turn on these devices. So the uh, voltage we are more concerned about is the voltage between the base emitter junction, the VBE voltage. So to get that voltage, what you need to do, you need to change your x-axis of the plot. Once you plot the current IB, by default, this voltage will be VBB, but you need to change that voltage to VBE. So the way you do it, if you have this node number, you just plot that. You just select that node in your x-axis. The emitter terminal is already at ground, so you don't need to signify that or like put that in. But ideally, the VBE is basically your base voltage minus your emitter voltage. All right. So once you do that, your curve will look something like this. And this should be around 0.7 volts. That will give you, this curve will give you the base current with the applied VBB. So what we really want, our main concern is where we are getting 5 microampere of base current at what voltage of VBB. So at what VBB voltage we are getting the base current of magnitude 5 microampere, because that is going to be our first set point or biasing point for this BJT. We are going to apply 5 microampere current at the base terminal, and then we are going to sweep the VCC voltage or VCE voltage to plot the IC current. So the way we do it is, let me erase this part so that I can draw that plot. So for the second part, what we are going to do is we are going to keep VBB fixed at a voltage where our IB current is 5 microampere. By keeping it at that value, we are going to sweep our the reverse active and the forward active operation. So the IV curve, if we are plotting IC versus VCE, again, we can, since VCC is essentially the, it's not going to be the exact value of VCE. So you need to change the x-axis from VCC to VCE. And again, the way to do it is you can define it as VC minus VE. So once you do that, you can get this plot from -5 to +10 volts. All right. And then we are going to increase the IB current from 5 ampere to 10 ampere, 10 microampere, 5 microampere, 10 microampere, 15 microampere, and then up to 20 microampere. So for these 4 IB currents, we are going to generate 4 different plots of IC-VCE curves in both forward bias and reverse bias direction. So they will look more like this, this IC-VCE plot. And the way we change this IB current is basically you can do it in a way that you know the voltage VBB required for the simulation for these particular IB values. So if you know, say, 1.5 volts of VBB will give you the 5 microampere base current. Then you can also go back to that plot and find where your 10 microampere voltage is, like what voltage should we apply to VBB to get that. Then we need 15 microampere and 20 microampere. And you can change this axis back to VBB to get those points on the x-axis, like where we are going to get these currents. And then you can change the parameter VBB. You can make it a parametric sweep. You can make it a DC sweep with those steps between the voltages so that you can get this IB current. And then you can plot the VCC, IC versus VCE plot in LT-SPICE. So that is pretty much the expectation of like how you simulate it. And once you are done with the simulation, we can move on to do it again in the experiment. So you build this circuit using this part BJT. So the part number is also 2N3904. It should be in your lab kit. I don't really exactly remember the parts number. If it's different, if the BJT chip that you have in your lab kit is different, you can still get this 3914 chip from the parts store. I would say, like, if you're using, when you're building the experimental setup, the circuit, you should definitely use the 3904 chip so that you can match your simulation data with your experimental data. So once you do that, we are basically going to have the same thing with once you're done with the NPN, we are going to do the same thing with PNP. So for the PNP transistor, let me draw the circuit so that you have a reference point here. So everything will remain almost the same. You have a source across the so you have, let me just draw it. So you have the same RB and RC resistors. The values will remain same, 1K and 100K. And then you have two sources but the ground terminal is on the collector side, and then you have to flip the voltage direction for the sources. So this is our VCC2 or VCC. I'm just denoting as 2 just to distinguish it from the NPN setup. And this is our VBB2. And you can see that this is our VBE voltage, which is going to be reversed now. Like this is going to be negative 0.7 across approximately. And the current will flow from base terminal towards outside, towards the resistor. And then this current will also be in the IC current will also be in the opposite direction. So for here, we are also going to do the same kind of simulation. We are going to repeat the exact same process. So we are first going to sweep the VBB voltage to get the IB versus VBE plot. And that plot should, in terms of shape, it should look similar to what we got for the NPN transistor. But the magnitude may be quite different in terms of in the PNP IB base current. And then once you do that, you are going to fix the VBB voltage for IB 5 microampere up to 20 microampere, just similar to the NPN. So we need 5, 10, 15, 20 microampere. And then we are going to draw that. We are going to simulate it again while sweeping VCC. So the VCC will sweep from from negative 10 to positive 5 volts. Or I think, yeah, scratch that. Let's do minus 5 to positive 10. Just similar to NPN, so that we will get the similar kind of plots over here. And in the reverse direction, we will get the similar kind of plot. So this is our IC and VEC. So once you do that, you can also, again, build the circuit. The model here for the BJT is going to be 392 and 3906. And it's the same way you right click on the component. When the new window appears, you select pick new transistor. And then in the table, you select 2N3906. And that is the device you are also going to use in the experiment to get the experiment done with the circuit. So our goal, once you get these plots, what we are going to do is we are going to try to find beta F and alpha F. So beta F, as you know, is going to be a collector current by base current, and alpha F is going to be collector current by emitter current. So from the IC VCE plot, you can find once the devices are in forward active mode, we can select the IC current, which is almost saturated and almost constant. And then for their corresponding IB, you can find the ratio beta F. And in similar manner, if you know beta F, you can calculate the alpha F from another equation, which is beta F by beta F plus 1. So once you do that for simulation, you can also do it for the experiment, where you can also generate, once you generate the ICVCE plots, you can again find the value of beta F and alpha F. So in our comparison table, you should include this comparison table in the conclusion, where you will have simulated beta F, alpha F, and for the reverse direction, you have beta R, alpha R. So you have your experimental calculation of these gains, and then you will have simulated um, numbers, simulation numbers for these beta F to alpha F and alpha R. Um, and what we're going to do, we are also going to verify their numbers from the datasheet for 3904 and 3906. So we are going to do it for both NPN and PNP BGTs. We are going to get all of their simulated gain results, the experimental gain results, and then their ideal datasheet numbers, so we can find that. So there is sort of like a characterization and sort of error calculation involved with that, how much our uh, values deviate from the datasheet numbers for these devices. So that's going to be one of the interesting discussion in the in this report. So in terms of plots, we basically need two plots: the base current versus base emitter voltage, and then the collector current versus the collector emitter voltage. In the report, you basically include all the simulated and the experimental plots together. So for the IB VBE plot, you simulated it and you also experimentally gathered the data. So plot those two simulated and experimental plots together in one graph. And then again, in a new graph, you put IC versus VCE plots for simulation and experiment. And repeat it again for the PNP BGT, where you will also get an IB VBE curve from your simulation and your experiment. And then IC VCE curve from your simulation and your experiment. So that is mostly and then the calculation for beta F and alpha F, beta R and alpha R, include those calculations in the results section. And in conclusion, include this table, what I just drew, that will have all the parameter values, gain values listed, and their deviation or error calculation also included. You should also include the schematics that you have generated, and then the circuits that you have built. In the report, you should have those figures or images included. Yeah, so that's pretty much everything about this lab. If you have any questions, feel free to email me or talk to me during the TA office hours. Hopefully, you should complete this lab successfully. Thank you so much for listening. Have a good best of luck with that.